We're going to take a look at question 11, which I'm deciding to call the spinning thing. So this question came up on the Leaving Cert paper this year, and it was met generally with consternation. So let's take a look at it. You're given there's a machine that's fixed at a point P. It's got a long arm, so let's use this for the long arm for a moment. So that's the long arm. And up at the end here, it's got a short arm attached up there like that. Okay, and there's an angle alpha, which is this angle here that it makes with the horizontal plane. Right, so that's the angle alpha there. And it's got an angle beta that it makes up here between these two. Alright, that's the point Q up at the top, that's the point R out here. And the controller can vary the angles alpha and beta from 0 to 180. So this angle here can go from 0 to 180. So in other words, if we keep this fixed for a second, this can go from 0, which will be in here. It can rotate all the way out to 180, but it can't go any further. So once it's straight there, that's as far as it can go. It can't go back this way. Alright, so it goes from 0 out to 180. So it can make a kind of a semicircle with its end. This end here can describe a semicircle like that. Okay. And if we fix that, let's say we fix it here, then this can also go from 0 to 180, this angle here. So it can start down here at 0, and then it can move all the way over to here, to 180, like that. And it can move all the way back again. Okay, so just to there. So it can live anywhere in the top half of it. This arm here can live anywhere in the top half of the plane. You can see just at the edge there that even if that's 0, the end point here is going to be down below what we might think of as the x-axis. If it's straight over like that, it's just out of shot there, then that's on the x-axis, right? If everything's straight like that. If it's folded back in this way, it's on the x-axis. Anything else, and it's describing a kind of a semicircle underneath the x-axis. Alright, and we're going to be asked at the end, what kind of a shape does this point describe? Where can it live? Well, it can live at the, if you fix this here flat across and just rotate the small arm, it can live anywhere on the end of that semicircle there. Alright, so let's go to the questions. So we're told that, we're going to sketch it in, so we're told that PQ, so this is my pen here, PQ, and we're told that it's 20, and we're told the QR is 12. Now, we want the tip of the arm R, so that's the end of this little thing here, right? So we want the tip of that to be 24 centimeters to the right of P. So we want it to be 24 centimeters across. 1 second there, no. So that's 24 across here, and we want it to be 7 centimeters higher than P, so we want this here to be 7. So let's draw in that extra kind of a triangle-y thing. Let's not worry for the moment about the fact that we seem to be splitting alpha in 2 bits, not in half, but in 2 bits. And beta is absolutely fine as it is. Okay, so looking at that, because this is a right angle triangle here, we have this and this, we should be able to find that using Pythagoras' theorem. Alright, so we should be able to find that distance, let's call it x. Once we have that distance there, we have 3 sides in this upper triangle, so we should be able to find that angle. Right? Remember, the cosine rule involves 3 sides and 1 angle. So step 1 is find x. Step 2 is using these 3 sides and this angle, using these 3 sides and we'll say this angle here, fill everything into the cosine rule, find what cos of this angle is, do the inverse cos, find what this angle is. From there, we want to find what alpha is. Well, to find what alpha is, let's find what this is here. Let's call this theta, and this here, so let's call this gamma. I think that's gamma. So theta we can find from the upper triangle using, we say, the sine rule. Gamma we can find from the bottom triangle using the sine rule, or just SOHCAHTOA, add the two of them and we get what alpha is. Alright, so by drawing everything in, and filling in as much as we can. It should be a little bit long, but reasonably straightforward to find what alpha and beta need to be. Okay, the second bit of the question, so B, C and D is where it gets really a bit more unusual. So B says, in setting the arm to the position described in part A. Well, let's just have a quick look at, I think the answers that we should get for part A are, well, we should get, I think, that this is 25. And that's all that kind of matters at the moment. Okay. In setting the arm to the position described in part A, which will cause a greater error in the location of R? So which one will result in R being further out? A 1 degree error in the value of alpha, or a 1 degree error in the value of beta? Okay. You may assume that if a point moves along a circle to a small angle, its distance from a starting point is equal to the length of the arc travelled. What they're talking about is this. If you have a point like that, you've got a rigid thing like this, right? And you have a point up on the edge, and you move it a little bit, right? So suppose it was there, and you move a little bit to this new position, right? Then it's saying you can assume that the distance between these 2 points is roughly the same as the distance of that arc. Now, they're not exactly the same. If you zoomed in, what you'd see is that the point here and your point here, the distance between them is a straight line, the arc is a bit curvy. But this is saying that because we're only looking at a 1 degree difference here, sorry about that, because we're only looking at a 1 degree difference here, then this is absolutely tiny. The curvature is very, very small, so we can assume, for kind of the sake of argument, that that distance and that distance are the same. So what it will be useful to write down now is what's the formula for the length of that distance. The length of that distance is 2 pi r theta over 360, where theta is measured in degrees. So the question is, is a 1 degree change in this going to result in that moving more than 1 degree change in this? Well, for each of them, pi is still pi, right? So 2 by pi, so pi won't make a difference. The radius is going to be different for the 2 cases. Alright, if I think of moving this by 1 degree, this thing is rigid. If I move this by 1 degree here, then this moves with a down 1 degree or up 1 degree. Okay, so that was the radius, it moved along, a radius of 25. If I keep this still and I move this by 1 degree up here, like that, okay, then it's not moving along a radius of 25 anymore, it's moving along a radius of 5. Okay, so the radius is going to change. Now theta in both cases is just 1, so 1 over 360. So the only thing the length is going to depend on is the radius. Okay, everything else is the same in both cases. So if we change alpha, we've got a change of 2 pi by the radius. So that radius is 25 times 1 over 360. If we change beta, we move that up a little bit, then the change is going to be 2 pi times 12 by 1 over 360. Okay, because if we change, just have a quick look back, if we change beta, this one here, right, if this is what we're changing, then we're moving this lad, we're keeping the pen fixed, and we're moving this yoke, so it's moving through a radius of that much, and that much is 12. Okay, so because the length of the arc, because we're moving both of them 1 degree, the theta is fixed, so as the length of the arc is changing, this one's clearly a lot bigger. Okay, and for part C, I'm not going to go through part C. Maybe it's one of the few things we'll discuss when we get back. Part C says, in certain positions, the location of R is more sensitive to changes in alpha. In other words, changes in alpha make it move more, and in other positions, changes in beta make it move more. Oops, sorry, should have had that in shot. So, in certain positions, changes in alpha make R move more, and in other positions, changes in beta to show you what we mean, suppose like that's one position, right? So that position there is one position that it could be in. Okay, another position it could be in, it could be like this, okay, or it could be like this. And some of the time changing this angle here will result in this moving further, and some of the time changing this angle here will result in this moving further. And the thing is, because you're moving them through the same angle, really the only question is which radius is bigger. So is it the radius from here out to R, or is it the radius from here out to R? So that's kind of what you're meant to spot and what you're meant to go on and describe. And one of these has a fixed radius. So is the distance from here to R fixed? Is it the same all the time no matter what position we're in? Or is it the distance from here to R that's fixed and it's the same? Right? So one of them is fixed, the other one's changing. So the question is, when the changing one gets smaller than the fixed one, it matters less. When the changing one gets bigger than the fixed one, it matters more. So we will discuss that a little bit more. And the fourth part, part D, which asks you to fill in on the diagram there. So this is the beginning position. So that's the pen. That's the little squidgy thing. Right? Now what we said was it might actually be helpful to physically get a pen. So if you know, what's useful is fix the pen and see where does the squidgy thing move. So we said if you fix the pen, the squidgy thing moves in a semicircle like that. Okay. And then what you do is you think of, well, as we move the pen, right, so move it a little bit. Okay. You can really think of, you can kind of get rid of the squidgy thing now, because no matter where the pen is, the squidgy thing is going to trace out a semicircle. So what you can really think of is, well, look, if I had a, I'm going to draw it in there. Let's draw it on a new page. Suppose this is where suppose that nice little circle is where the pen is starting from, right? So the squidgy thing traces out its semicircle, like so. So what you can think of now is, as I rotate the pen around here, think of that as being stuck onto the pen, right, and covered in ink, and what kind of a trail would that leave? So it's obviously going to leave some kind of a semicircular trail over here. So this bit is going to move around like so, and this outer bit is going to move around like so. And then the last thing is, well, what's going to happen over on the far side over here? So on the bit of the tablecloth here, which I won't write on with permanent marker. Here, the semicircle is down below. Once I bring it along, where is the semicircle going to be? Is the semicircle still going to be down below here, or is it going to be up above? So that's really the only question that you have left to answer. And then this area in here, this kind of weird half donut area, is the area where the end of the squidgy thing can actually have a go off that.